All right, so you know how much I love a good deep dive, and this one is all about polymers. Like I was looking at the stuff you send over, a textbook chapter on ideal chains, and it just seems like they're everywhere.
Yeah.
Like we're practically swimming in them.
Polymers are pretty ubiquitous.
So before we get lost in this world of long, chain-like molecules, what exactly are we dealing with here? Give us the polymers 101.
Okay, well, imagine like a really, really long chain, kind of like those bead and string toys,
Oh, okay.
but on a molecular level. So each link in the chain is what we call a monomer. And when these monomers link up, they form polymers, these macromolecules, huge molecules.
Okay, so it's like we're taking these simple building blocks, these monomers, and just stringing them together to create these giant, well, polymers, and you said they're everywhere.
They really are. Think about it. Plastics, rubber, even DNA, proteins, they're all polymers.
It's mind-blowing. So something as simple as a chain of repeating units can result in materials as different as a plastic bottle, and like you said, the DNA that holds our genetic code.
That's incredible. Okay, so where do these ideal chains you mentioned fit into all of this?
So ideal chains are kind of like the starting point for understanding polymers. Imagine a polymer chain where there are absolutely no interactions between the monomers.
So, like, they're just chilling.
Mhm.
No drama, no attraction, no repulsion, just pure freedom of movement.
Exactly. They're free to wiggle, bend, and rotate in any way imaginable, kind of like those bendy straw toys.
Okay, I'm picturing it. So it's a simplified model that helps us wrap our heads around these complex molecules. It is. By ignoring those complicated interactions, we can really start to understand the fundamental behavior of polymers without getting bogged down in the details. It's like starting with a sketch before diving into a detailed painting.
I like that. You need that basic outline before you can add all the colors and textures.
Yeah.
Okay, so with ideal chains, we're throwing out those monomer interactions. What else makes them unique?
Their flexibility. And the key to this flexibility lies in something called torsion angles.
Torsion angles. Okay, break it down for me.
So these angles basically determine how easily monomers can rotate around the bonds that hold them together. You can visualize this with figure 2.1. There are two primary positions or states these torsion angles can take.
All right, I'm looking at figure 2.1. What are these two states?
First, there's the trans state, where the monomers are on opposite sides of the bond. Think of it as the most relaxed, natural position. Like in those bendy straws, they naturally want to stay straight unless you bend them.
Okay, so trans is like our chill, laid-back state. What about the other one?
The other state is called the gauche state. In this state, the monomers are kind of crammed together on the same side of the bond.
So instead of chilling on opposite sides, they're like, hey, let's all hang out on this side. It'll be fun.
Something like that. But it actually creates what we call steric hindrance. Basically, the monomers are bumping into each other.
Ah, so gauche is more like that cramped feeling you get when you try to stuff too many clothes into a suitcase.
Precisely. And this gauche state takes more energy because those monomers are essentially fighting for the same space.
Got it. So trans is relaxed, gauche is crowded. Now, how do these different states, these trans and gauche positions, affect the overall shape of our ideal chain?
That's where it gets even more interesting. Because of these different torsion angles and their energies, a single chain can actually take on tons of different shapes, which we call conformations.
So even though we're ignoring the drama between the monomers, we still get a lot of variety in how the chain can actually look.
Absolutely. And to measure the size of these shapes, these conformations, we use something called the end-to-end distance, or R.
End-to-end distance. Sounds pretty self-explanatory, just measuring from one end of the chain to the other, right?
Exactly. Figure 2.3 shows it visually.
Okay, so if we've got all these different possible shapes, all these conformations, does that mean R is going to be different for each chain?
You got it. That's why we use something called the ensemble average, which we represent with these neat little angle brackets in LT and GT. It's basically the average of R over all the possible conformations a single chain could have.
Okay, I'm following. So instead of measuring one chain at a time, we're getting a sense of the average size, taking into account all those possible shapes. Clever. So how do we go from this general idea of an ideal chain to actually modeling and understanding their behavior?
We use models, of course, and we'll
Mhm.
start with the simplest one, the freely jointed chain model. Take a look at figure 2.5.
Okay, figure 2.5, got it. So what makes this freely jointed chain so special?
Well, in this model, we assume that each bond vector, which is just the line connecting two monomers, can point in any direction it wants. It's completely independent of its neighbors.
So complete and utter randomness. It's like taking that bendy straw and shaking it like crazy. It can bend and twist in any direction.
Exactly. And despite this randomness, we get this really neat relationship. The mean square end-to-end distance, or NLAT, RNGAT, is proportional to the number of bonds N in the chain and the square of the bond length L.
So longer chains with longer bonds mean a bigger inelt RNGA. It's like saying the more links you add to your chain and the longer each link is, the wider you can potentially spread it out.
Precisely. But, and there's always a but, real polymers aren't quite as chaotic as our freely jointed friends here.
Oh, so our model isn't perfect.
No model is. Real polymers have a bit more order, a bit more structure. Their neighboring bonds like to have a say in which direction they point. It's not total anarchy. And that's where Flory's characteristic ratio comes into play. We symbolize it with C-Che.
C. Okay, this sounds intriguing. What does this ratio tell us about real polymers then?
Think of C as a measure of a chain's local stiffness. It basically tells us how much larger the actual mean square end-to-end distance is compared to what our simple, freely jointed model would predict. Figure 2.4 gives you a good visual representation of this.
So if I'm understanding this right, a higher CC means a stiffer chain, like less bendy straw and more. Well, I'm not sure what's less flexible than a bendy straw.
Maybe a metal rod.
Yeah, something like that. Okay, I get it. Higher CC, less flexible. And is there a way to measure the stiffness directly?
There is. We use something called the Kuhn length, denoted by B. Imagine it as the effective size of a monomer, but this effective size takes into account the chain's stiffness.
So we're essentially saying, okay, real polymers aren't perfectly freely jointed, but we can still think of them that way if we imagine each segment as a Kuhn segment, a segment that's a bit bigger and clunkier to account for that inherent stiffness. It's like a way to simplify things, right?
Exactly. And the cool thing is that Table 2.1 actually shows C share in B for a bunch of common polymers. You can see how much their flexibility can differ.
It's like a flexibility ranking for polymers. It's great stuff. Okay, I'm ready to move on to the next model. We've tackled the freely jointed chain. What other tools do we have in our polymer modeling arsenal?
Let's step things up with the freely rotating chain model, which is also illustrated in Figure 2.5. In this model, we're keeping those fixed bond lengths and bond angles from before, but now we're letting the monomers spin around their bonds a bit more freely.
So our bendy straw can't bend backward on itself anymore, but it can still twist and turn.
You got it. And this model introduces a really interesting concept. The idea that as you move along the chain, the influence one bond's direction has on another starts to fade away.
So it's like that game where you whisper a phrase from person to person. By the time it gets to the end of the line, the message is totally different.
Exactly. And this fading influence is related to what we call the persistence length, or ELP. You can think of it as the length over which those bond directions basically forget about each other.
Bro, ELP, got it. It's like a molecular game of telephone. The message gets lost along the way.
And the formulas in the chapter, they actually connect this ELP to the bond angle and C-Che. It all ties together beautifully. But this makes me think, for really stiff polymers, do you think this model still works?
Good question. I mean, I'm picturing DNA again. That thing is pretty rigid. Trying to make a bendy straw out of a metal rod. Not gonna happen.
You're exactly right. For those super stiff polymers, we turn to the worm-like chain model. This one's defined by its persistence length, LP. And get this, the Kuhn length in this model is just twice the ELP.
Twice the ELP. So for these stiff chains, the effective size of a monomer is basically double the distance over which it can remember its neighbor's direction. That makes sense.
And this leads to a very large SAT1, reflecting that inherent stiffness.
So many models. It's like we have a whole toolbox for understanding these chains. We've covered freely jointed, freely rotating, and worm-like. Are there any other models we need to add to our repertoire?
There are a couple more. The hindered rotation model and the rotational isomeric state model. These models acknowledge that rotating around those bonds isn't always a free-for-all. Remember those gauche states where monomers get a little too close?
Right, those higher energy crowded states. So these models take those energy barriers into account. They're getting even more realistic.
Precisely. And the rotational isomeric state model that one's the superstar of the group. It's the most successful model for really detailed calculations. And thankfully, Table 2.2 comes to our rescue with a nice summary of all the models, their assumptions, and what they predict.
Oh, thank goodness for Table 2.2, a lifesaver for those of us who don't speak fluent polymer science. Okay, we focused a lot on end-to-end distance, or R. Are there any other important ways to size up these ideal chains?
There is. We also have the radius of gyration, or RG. You can see it in Figure 2.6.
RG. Okay, give me the lowdown. What is this radius of gyration all about?
Imagine a bunch of kids scattered randomly on a playground. The radius of gyration is like measuring the average distance of all those kids from the center of the playground.
Okay, so instead of measuring the whole playground, we're looking at how spread out the kids are from the center on average.
Exactly. And for a nice linear ideal chain, the mean square radius of gyration, NLT, RG, and GT, is actually just 1/6 of the mean square end-to-end distance, NL time RGT.
1/6. It's amazing how these precise relationships just emerge from these models. Okay, so we've got all these theoretical models, but how do scientists actually study real polymer conformations in the lab? It's not like they can just grab a chain and measure it with a ruler, right?
That's where things get really high-tech. Scientists use a powerful tool called scattering experiments.
Scattering experiments. Okay, I'm intrigued. Tell me more.
Imagine shining a beam of light, or even X-rays or neutrons, at a polymer. Then we analyze how that beam scatters off of it.
So it's like we're using light or X-rays or neutrons to see the polymer chains.
Exactly. But for this to work, we have to create contrast. We need a way to distinguish the polymer from its surroundings. Often this means dissolving the polymer in a special solvent.
So we need to make the polymer stand out from the background, kind of like how a chameleon changes color to blend in, except we're doing the opposite.
You got it. And here's where it gets even cooler. A really important concept in these experiments is the scattering wave vector, which is denoted by Q.
Q, okay, another variable to add to the mix. What does it represent?
So Q is essentially a measure of how the direction of our beam, whether it's light or X-rays or neutrons, changes after it hits the polymer. It's related to the scattering angle, the angle at which the beam changes direction, and the wavelength of the beam itself.
So if our beam was a tennis ball bouncing off a wall, Q would tell us how much the ball's direction changed after the bounce.
You got it. And we can use this Q to calculate something called the form factor, which we symbolize with PQ.
Okay, things are getting a little complicated again. What in the world is a form factor?
Think of the form factor as a fingerprint of the polymer's shape. It basically describes how the intensity of the scattered beam varies with Q, and this gives us valuable clues about the polymer's size and shape.
So by analyzing how that beam scatters at different angles, we can actually figure out what our polymer chain looks like. That's incredible.
It is pretty amazing. And at small scattering angles, meaning small values of Q, the form factor doesn't even care what specific chain model we're using. This is where we can figure out the radius of gyration, or RG.
So even without knowing if we're dealing with a bendy straw or a metal rod, we can still get a sense of its overall size. That's really useful.
It is. But as we go to larger scattering angles, larger values of Q, the form factor starts to reveal more about the chain's specific shape.
Ah, so the wider the scattering angle, the more we can distinguish between those different shapes, those different conformations. It's like the form factor becomes a more detailed fingerprint.
Precisely. And for that simplest case, that ideal linear chain we talked about, the form factor is described by something called the Debye function.
Debye function, got it. And I'm assuming there are ways to make this function a bit more manageable depending on those scattering angles.
There are. For both small and large Q values, we can use simpler expressions to approximate the Debye function.
Q, that's a relief. I think my brain needs a break after all that math. But, it's incredible how these seemingly simple models can be so insightful. Who knew that chains of molecules could be this complex?
It really is fascinating. But there's a catch. Ideal chains are, well, ideal. They don't capture the full picture of how real polymers act with all their quirks and interactions.
This brings me to my next question. How do these real-world polymers, with all their messy relationships, deviate from these nice, neat models?
You said it. Real life is messy.
It really is.
And polymers are no exception. When we start factoring in those monomer interactions, things get a lot more.
Let's get messy then. What kind of craziness happens when these monomers start interacting?
Well, picture a crowded room full of people all trying to move around.
Okay, I've been there.
It gets tricky, right?
Yeah.
And monomers, just like people, they have their own personal space.
They're not big on sharing.
Not really. And this is what we call excluded volume.
So it's like each monomer has this little invisible bubble around it, and they're all trying to avoid bursting each other's bubble.
Exactly. It's all about personal space.
Yeah.
And to really get a handle on this bubble bursting aversion, we can use something called the Mayer function.
The Mayer function. Sounds intense.
It's not as scary as it sounds. Figure 3.4 actually gives you a great visual representation of it. Basically, this function helps us figure out how much two monomers like or dislike being near each other at a given distance.
So it's like a molecular friendship bracelet. The closer they are, the more intense the feeling, whether it's love or hate.
I like that. You're on the right track. At very short distances, the Mayer F function is strongly negative, meaning those monomers are basically yelling, "Get out of my space."
Yeah.
But as they move a bit further apart, the function can actually become positive, which hints at a bit of attraction.
It's like that push and pull, that constant negotiation between stay away and come closer, maybe.
Hmm.
So how do we go from this function to actually understanding the overall impact of these interactions?
We condense it all down to a single parameter, the excluded volume, denoted by V,
Little v.
little v, and it basically sums up the net effect of those monomer interactions, taking into account both the repulsion and the potential for attraction.
So v is like the relationship status of our monomers.
In a way, yes, and the sign of V, that's key. A positive V means those monomers are all about that personal space they're repelling each other, which leads to more extended, spread-out chains.
Okay, so positive v, think like a mosh pit. Everyone's jumping around, but no one wants to actually touch.
Exactly. Now, a negative V, on the other hand, means there's attraction, so the chains end up more compact, cozier.
Negative v. We've moved on to the slow dance. Everyone's clinging to their partner. Okay, I'm getting the picture. So we've got our monomers, and we know their relationship status is determined by this excluded volume v. Now, how does the environment they're in play into all of this?
That's a great question. The solvent, the liquid our polymer's hanging out in, plays a huge role. We can actually categorize solvents based on how they interact with our polymer.
So it's like different moods on our molecular dance floor. Some solvents get everyone in the mood to mingle, while others make everyone want to just hang out with their close friends.
I like the way you think. Let's start with what we call a thermal solvents.
Thermal.
In these solvents, it's all about repulsion. The monomers can't stand each other. They're like tiny billiard balls constantly bouncing off each other. No love lost, just pure excluded volume.
So a thermal solvents bring out the hardcore mosh pit vibes. Got it.
Exactly. This usually happens at high temperatures, by the way. Lots of energy, lots of bouncing around.
Makes sense. Okay, what about those solvents that encourage a bit more interaction, a bit more let's be friends?
Those would be our good solvents.
Good solve.
In these solvents, our monomers actually prefer to be around the solvent molecules rather than each other. It's like adding a bunch of really cool new people to that dance floor. Suddenly, the monomers aren't so interested in clinging to each other. This still leads to a positive excluded volume, but it's smaller than in those thermal solvents.
So those repulsive vibes are still there, but the solvent is playing matchmaker, trying to smooth things over.
Precisely. Now, there's one more type of solvent we need to talk about, and it's a special one. The theta solvent. Imagine a dance floor where everything's just right. The music, the lighting, the vibe. Suddenly, the attraction and repulsion between our monomers are perfectly balanced.
It's like the universe achieved molecular harmony.
Exactly. And this magical state, it happens at a specific temperature, which we call the theta temperature.
The theta temperature.
Yeah. At this temperature, the excluded volume basically disappears. Poof. It's like it never existed.
So it's like our polymer chain is living its best ideal chain life at the theta temperature.
Precisely. And scientists actually use this theta state as a reference point to understand how polymers behave when things aren't quite so balanced.
That makes sense. Okay, so we've got a thermal, good, and theta, a whole spectrum of solvent personalities. What about those bad solvents we hear whispers about? Do those monomers ever get to embrace their inner introvert?
They do. In poor solvents, the monomers decide their fellow monomers are the only ones they can trust. It's like the music turned terrible, the lights are way too bright, and suddenly all they want to do is huddle together and avoid the solvent as much as possible.
It's like that awkward moment at a party when you and your friend just want to disappear into a corner and avoid eye contact with everyone else.
Exactly. And this solvent aversion can get pretty extreme. Sometimes the monomers get so antisocial that the whole polymer collapses in on itself, forming a dense little globule.
A globule, like a hedgehog rolling itself up into a ball.
Perfect analogy.
Yeah.
And, of course, the most extreme case of a poor solvent is a non-solvent. In this scenario, the dislike is so intense that the polymer just gives up and falls out of the solution completely.
It's a molecular breakup. Okay, so we've got these real-world polymers, and we know they come with baggage complex interactions, a whole range of solvent personalities. How do scientists even begin to make sense of it all?
That's where some serious brain power comes in. One of the most successful and influential theories we have for understanding real polymer behavior is the Flory theory.
Flory theory. Okay, I'm ready to be impressed. Hit me with it.
So imagine our polymer chain with its N monomers happily spread out in a volume of size R. Flory theory assumes that these monomers are basically evenly distributed within that space.
Evenly distributed.
Yep, like a cloud of gnats just kind of hanging out. And then it considers both the energetic and entropic contributions to the chain's free energy.
Okay, so we're thinking about those energetic interactions that push and pull between monomers, but we're also factoring in the chain's desire to wiggle and explore all those different shapes, just like with those ideal chains we talked about earlier.
Exactly. The energetic contribution comes from those excluded volume interactions we talked about, represented by our friend V. And the entropic contribution comes from the chain's conformational entropy, the number of ways it can wiggle and bend.
So it's a balancing act. On one hand, we've got those monomers with their personal space issues, and on the other hand, they've got that natural urge to just dance around. How does Flory theory find that compromise?
It's all about finding the sweet spot, the point where the total free energy of our chain is minimized.
Okay, so minimize the free energy. Got it. And what does that tell us about our real-world polymer?
When we do that, we get a prediction for the chain's size. And guess what? It's actually bigger than we'd expect from those idealized models.
So those excluded volume interactions, they actually puff up the chains a bit compared to those more laid-back ideal chains.
Yeah. Exactly. And get this, Flory theory predicts that the chain size, R, scales with the number of monomers, n to the power of 3/5.
3/5, that's so specific.
It is. And this 3/5 power law, it's been confirmed experimentally over and over again. It's a cornerstone of polymer science.
Wow, 3/5, a seemingly random fraction that holds the key to polymer behavior. That's incredible.
So Flory theory really nailed it then. It cracked the code for real polymers.
It's definitely a rock star in the polymer theory world. It's remarkably accurate, especially considering its simplicity. But it's still a model, and like all models, it has its limitations.
Right, no model is perfect. What are some of the things Flory theory might be missing? Well, for one, Flory theory is a mean field theory, which means it assumes that those monomers are always pretty evenly distributed. In reality, things can get a bit more clumpy or spaced out. And it also doesn't really account for certain correlations between monomers, especially those that are far apart on the chain.
So it simplifies things a bit, which is why it works so well, but those simplifications come at a cost. There are some finer details it might be glossing over.
Right. But overall, it's a powerful tool.
It sounds like it. But we've been focusing a lot on those good solvent conditions, those let's mingle environments. What about our poor introverted polymers and those bad solvents? Does Flory theory have anything to say about their behavior?
It absolutely does. In those bad solvent conditions, remember, that's where the monomers would rather stick to each other than interact with the solvent. Flory theory predicts that the chain collapses into that globule we talked about, that little ball of monomer misery.
Right, the molecular hedgehog.
Exactly. And here's the kicker. The size of that globule, it also scales with the number of monomers, but this time it's to the power of 1/3.
1/3. So instead of that 3/5 power law for our happy swollen chains, we've got a 1/3 power law for our collapsed introverted chains. It's all about those exponents.
Exactly. That 1/3 power reflects the chain's attempt to minimize its contact with the solvent it dislikes so much. It's all about reducing that surface area, creating that cozy little monomer huddle.
It's amazing how this one theory, this Flory theory, can explain such a wide range of behaviors, from those sprawled out, mingle-happy chains to those tightly wound introverted ones. It's pretty elegant when you think about it.
It really speaks to the power of a good theoretical framework. But there's one crucial aspect of polymer behavior we haven't even touched on yet. Their dynamics.
We've been talking about these polymers like they're frozen in time. But in reality, they're constantly moving and changing, right? It's not all just static poses on the dance floor.
Exactly. Things are twisting, turning, and grooving.
It's time to get those polymers moving. I'm ready to see some action on this molecular dance floor.
Well, get ready, because polymer dynamics are where things get really interesting. We're moving beyond those static pictures of chains and into the world of wiggles and twists and turns, a real molecular mosh pit.
Okay, I'm picturing those long chains all tangled up, bouncing off each other. It sounds like a wild party.
It can be pretty chaotic.
Yeah.
But to model something this complex, we need to start with a slight simplification. Imagine our polymers in a nice viscous fluid, kind of like those bendy straws we talked about. But instead of air, they're swirling around in honey.
Okay, I can picture that slow and gooey. A much more relaxed vibe than that mosh pit I had in mind.
We have to start somewhere. And this brings us to the Rouse model, a classic in polymer dynamics. Imagine this. Our polymer chain is transformed into a series of beads connected by springs.
Beads and springs. Okay, I'm visualizing it. So each bead represents a bunch of monomer.
Exactly. And those springs, they represent the entropic elasticity of the chain. Remember how we talked about those chains wanting to wiggle and maximize their randomness?
Right, that was back in our ideal chain days. So we're still holding on to that concept of entropic elasticity, but now we're applying it to movement. It's like those chains just can't sit still.
Precisely. They have that inherent drive to explore all those different shapes. And what's so great about the Rouse model is its simplicity. Each bead is only influenced by two things: the drag force from that honey-like fluid around it.
Okay, that makes sense. It's like trying to move through honey, not so easy.
Exactly. And then the other thing influencing it is the restoring force from those springs connecting it to its neighbors.
So it's a constant push and pull between those two forces. But I have to ask, no crazy excluded volume effects here. No monomers bumping into each other like in a real mosh pit.
For the basic Rouse model, no. Remember, this is a simplified model. There are more complex versions out there that try to incorporate those excluded volume effects, but they get pretty hairy, mathematically speaking.
Okay, I'm happy to stick with the simpler version for now. So what kind of cool insights does this elegant Rouse model give us? What does it tell us about how polymers actually move?
One of the key takeaways is that a polymer's motion isn't just one thing. It's a whole spectrum of movements happening at different speeds, each with its own relaxation time. Think of it like this. The whole chain can do this slow, graceful sway, while individual monomers are doing their own little jigs at a much faster pace.
So it's like an orchestra with different parts of the chain playing at different tempos. I love that.
Exactly. And these relaxation times, we can actually measure them in the lab.
Really? How do we do that? Are we just shining a flashlight at these polymers and timing their moves with a stopwatch?
Not quite. We use techniques like dynamic light scattering. Imagine shining a laser beam at a solution of polymers and then looking at how that light scatters off of them. Kind of like those scattering experiments we talked about earlier, but this time we're interested in how that scattered light fluctuates over time. And guess what? Those fluctuations actually tell us about those different speeds, those relaxation times.
That's amazing. So we're using light to spy on our molecular dancers. And the Rouse model is like our guidebook, helping us decode all those fancy moves.
You got it.
Yeah.
But of course, we can't forget about our real-world polymers, those chains that love to bump and grind on the dance floor. How do those excluded volume effects we talked about earlier change the dynamics?
Right, because honey or no honey, those monomers still have their personal space bubbles, right?
Exactly. And those bubbles, that excluded volume, it tends to slow things down, especially for those larger scale movements of the whole chain. Imagine trying to waltz in a crowded room. It's a lot harder to move gracefully when you're constantly bumping into people.
So it's like our honey-filled dance floor just got a whole lot more crowded. Poor polymers, they're really having to navigate a lot.
That's a great way to put it. And this crowding effect, this slowing down, is actually captured by the Zim model, which is a modification of the Rouse model that takes into account those excluded volume interactions.
So Zim takes Rouse to the next level, adds a bit of that real-world messiness.
Precisely. And the Zim model makes some interesting predictions. It tells us that the relaxation times for real polymers are actually longer than what the Rouse model would predict, especially for those slower, large-scale motions.
Because those crowded waltzes take more time to execute. It makes perfect sense.
Exactly.
It's amazing how these models, even the simplified ones, can give us so much information about how polymers actually behave. It really shows how powerful physics and math can be when it comes to understanding the world around us.
It's pretty incredible, isn't it?
It really is. Well, I think we've given our listeners a great overview of the fascinating world of polymer chains, from their static shapes to their dynamic behavior. We've covered it all.
We have. We've seen how those models, those elegant equations, can help us understand the behavior of these seemingly simple but incredibly complex molecules that are all around us.
And that's what I love about these deep dives. We take something familiar, like, say, a plastic bag or a rubber band, and we uncover this hidden world of polymers with all their quirks and complexities. It's a whole new way of looking at things.
It really is. So the next time you encounter a plastic toy, a strand of DNA, or even a piece of chewing gum, I hope you take a moment to appreciate those intricate polymer chains that give these materials their unique properties.
I know, I will. They're more than meets the eye. Well, on that note, it's time to wrap up this deep dive into the world of polymers. Thanks for joining us on this journey.